So, good afternoon, everyone. Welcome to the week 7 problem solving session for the course Waste to Energy Conversion. The course instructor is Professor P. Mondal from IIT Roorkee, and my name is Asma Parveen, and I am one of the TA for this course, and I am a PhD scholar in IIT Kanpur. So, in week 7, the first lecture was the second part of the fermentation, and then there was two tutorial. One was based on anaerobic digestion, and the second was on fermentation, and last two lectures was on trans-esterification. So first we are going to see a very brief recap of what was there in week 7 lectures, and then we will try to solve the previous year assignment questions. So just let me share my screen. So this is the first lecture of week 7. It is on fermentation. We have seen the in the first lecture of fermentation in week 6. So already fermentation, these topics have been covered. Fermentation and energy production, production of ethanol from different feedstock and pre-processing step, production of ethanol from starchy crop, and production of ethanol from lignocellulosic biomass, in which we have done seen the pre-treatment and detoxification and hydrolysis. And in this lecture, we are going to see fermentation, microorganism, and product recovery, followed by ethanol production through gasification route and butanol production from lignocellulosic biomass. So here reaction are given like how cellulobioes and xylobioes are converted to ethanol, and the amount of that the ethanol productive or amount of ethanol produced per unit of substrate utilized per unit of time, it is ethanol productivity, and it is determined when the ethanol concentration is maximum, and it is determined using this formula. And there are some of the microorganisms which are used for fermentation of lignocellulosic biomass. So these are some of the bacterial strains which are being used, like Zymomonas mobilis and E. coli. These are the strains which are used, but genetic modification have been done on some of the strains of bacteria and yeast which are capable of fermenting both pentose and hexose. Uh, some of the bacterial strains, are able to ferment only a particular type of carbohydrate and sugar. So genetic modification is done so that it can ferment more than one carbohydrate, more than one sugar type. So here is the route for product recovery. So there are two routes. First is the low temperature route, in which membrane processing or molecular sieve water absorption is done to extract the ethanol. Next is the thermal route, in which fermenter, then steam stripper, followed by distillation tower and vapor phase drying is done. So please go through these. Next is the butanol production from lignocellulosic biomass. So some of the strains of bacteria which are um, capable of converting broad-ranging carbon sources to fuels and chemicals are Clostridium specific, and butanol is a major co-product of acetone, butanol, and ethanol fermentation, as the typical proportion of acetone, butanol, and ethanol are 3:6:1. So please go through all the theory. So for the next is recovery of the butanol. So the first method for recovery of butanol is by adsorption. So from the fermenter, the butanol goes to adsorption column, in which the butanol is adsorbed on the column, and then after saturation of the column, it is regenerated by using heat. So this adsorption column can be used again and again. Next is the recovery by pervaporation, in which a semi-permeable membrane is used, which allows specific compounds to pass through it. So they are separated by a membrane. So here we can see that feed is given, and from the membrane only species A can go to the other side, and finally the everything which gets passed through the membrane is called permeate, and everything that is retained in the membrane is known as retentate. So the pervaporation is based on high selective membrane, and they are generally costly than adsorption. Next is butanol recovery by supercritical fluid. So these supercritical fluid can easily dissolve butanol and it can be extracted. Next is the gas stripping, in which after fermentation gas plus gaseous vapor goes to condenser, and here the gaseous product condenses and we get the butanol as the product, and the remaining gas is used for recirculation. Next is the liquid-liquid separator. So here some sort of solvent is used to dissolve the butanol and extractors. So some of the extractants used which have been recovered are corn oil, vegetable oil, hexanol, aromatic hydrocarbons, and etc. Next is by distillation. Uh, so distillation requires higher energy because the boiling point of butanol is higher than that of water. So it needs to be boiled at around 117.7 degrees centigrade. So here are some of the advantages and disadvantages of various method of butanol recovery are given. Like first is adsorption. It's the advantage, it is very easy to operate and less energy intensive. But disadvantages is it has very high material cost and high absorption regeneration cost because the exhausted column have to regenerate it by washing with some reagent. Next is the distillation. So distillation is a traditionally used method. It requires less infrastructure, but it has very high operation cost and highly energy intensive. Next two methods are gas stripping and liquid extraction. So gas stripping has a low selectivity and lower efficiency, but it has easy to operate. And there is no membrane falling in gas stripping like that is in perforation. Next is the liquid extraction. It is lesser energy intensive than other method, but it has high operation cost. So next is perforation. It is very vulnerable to temperature sensitive compounds and cell, and it is very high cost and very high costly membranes are used. Next is a supercritical fluid extraction. Now it is very new field and it needs more research to be used. And so here some of the bacterial strains which are used for butanol production is given for different feedstock. So let's move to the next one. So this lecture and second and third is on tutorial on anaerobic digestion and tutorial on fermentation. So we will see the questions based on this topic in the assignment questions. Let's go to transesterification. So transesterification is the process. So this is the first slide. So it is the process in which fats are converted to form fatty acid alkyl ester. This is the biodiesel and glycerine. So here it is a plant oil which reacts with methanol and some catalyst is used and we get fatty acid methyl ester which is the biodiesel and we get a additional byproduct which is the glycerol. So the reaction requires some heat and a strong base catalyst like NOH or KOH and transesterification will take place. So organic waste for transesterification, it can be bio oil, it can be cooking oil, it can be waste oil seeds, or it can be recycled grease, and it can be and through upgraded transesterification we will get biodiesel. So here a flow chart is given for production of bio oil from bio seeds. For the two conventional methods are expeller press method and solvent extraction method, and the advanced method are ultrasonic assisted extraction and supercritical fluid extraction method. So these are the oil press and solvent extraction method photos given. So some of the factors which affect the oil extraction is the type of solvent which you are using, biomass to solvent ratio, temperature, what is the extraction method used, what is extraction time and moisture content and particle size and shape. So here are the different processes and their advantages and disadvantages are given. So please go through all these. So, some of the properties of biodiesel is that it should have a high cetane, relatively higher cetane number. It should have very low sulfur percentage. And please go through all these. So let's move to the last lecture. So there are 5 steps which are involved for conversion of fat and oil into methyl ester and glycerol. First is acid uh, esterification, which is a pre-treatment. Then there is trans-esterification, methanol recovery, biodiesel refinery, and glycerine refining. So here each step is given. Please go through all these, and now we will go directly to the questions. So just give me a minute to reshare my screen. Just give me a minute, I got disconnected. So, as I already told you, the course instructor is Professor P. Mondal from Department of Chemical Engineering, IIT Roorkee, and my name is Asma Parveen, and I'm a PhD scholar at IIT Kanpur. So, let's go directly to the questions. So, the first question is, the maximum theoretical ethanol yield is given by, so we have been given 4 formulas and 4 options, and we have to find out which is the correct formula to find out the maximum theoretical ethanol yield. So we will discuss the solution in 2 minutes. So, hi, Swagata. So, this is the first question. We have to find out the maximal theoretical ethanol yield. So, four options are given. So, I'll wait for 2 minutes. Please write your answer in the chat box and then we will discuss this question. So, let's see what is the answer. So, correct answer is B. So, here we can see uh, for the maximum theoretical ethanol yield, it is given by ratio of ethanol produced in the reactor in grams divided by initial sugar in reactor into 0.511 into 100. So this is the formula. So B is the correct answer. So let's move to the next question. So the question is biological root uses dash bacteria for the production of ethanol from lignocellulosic biomass. We have to find out the most suitable option. Whether is Pichia stipes, Clostridium. Next is the Candida parapsilosis and Lactobacillus. So we have been given four options and we have to select the bacteria which is used for production of ethanol from lignocellulosic biomass. So again we will wait for 2 minutes and see which is the correct answer. So the bacteria which is used is Clostridium. So B is the correct answer. So this bacteria is used for ethanol production from lignocellulosic biomass. So B is the correct answer. So let's move to the next question. So this is a numerical. In a high rate biogas plant, food waste is anaerobically digested to produce biogas. The slurry contains 10% of solid food grain. The elemental composition of the food grains on dry basis is carbon 60%, hydrogen 7%, oxygen 25%, and nitrogen 8%. And around 80% of the food grains are converted to biogas, and uh, converted hydrogen forms methane. If the flow rate of the slurry is 500 liters per day, calculate the rate of biomass production. So we have been given the solid content of the slurry, and we have been given the elemental composition of the food grain, and we have to find out how much biogas is produced per day, and biogas consists of CO2 and methane. So we'll wait for 2 minutes and then we will see how to solve this question. So let's see how to solve this question. So we have been given the flow rate of slurry is 5,000 liters per day, and the dry solid food grain used is, sorry, is around 10%. It is given as 10% of the solid food grain. So it will be 10 by 100 into 5,000. So we will get 500 kg. Now we have to assume the density of the slurry. We will assume it as 1 kg per liter. So now from this 500 kg, we will find out how much carbon, hydrogen, oxygen and nitrogen is present. So in 500 kg solid food grain, carbon present is 60%. So 0.6 into 500. So that will be 300 kg. Hydrogen is 7%. So it will be 0.07 into 500. That will be 35 kg. And we have oxygen as 25%. So that will be 0.25 into 500. 125 kg. And finally we have nitrogen as 8%. So that will be 0.08 into 500, which will be 40 kg. So we have calculated how much carbon, hydrogen, oxygen and nitrogen is present in the food grain, 500 kg of the food grain. Now we have to find out how much biogas is produced. And also we can see that a statement is given that around 80% of the food grain are converted to biomass and all the hydrogen forms methane. So from this 35 kg of the hydrogen, it is used to form, all of this is used to form methane, and around 80% is of the food grain is used to form biomass. So let's move to the next slide. And the food grain is organic waste which will generally consist of carbon and hydrogen. So it is given that 80% of food grains, these are converted to biogas. So and food grains are organic waste, so carbon converted to biogas will be, so we were having around, carbon is 300 kg and hydrogen is 35 kg. Hydrogen is 35 kg and carbon is 300. And 80% is converted, so it will be 240 kg of carbon is converting, and hydrogen converted to biogas. So we have 35 kg of hydrogen, so 35 into 0.8, it will be 28 kg. And also it is given that So let me go to that statement. So around 80% of the food grains are converted to biogas. So the carbon and hydrogen which converts to biogas will be 80% of what we have calculated from the dry mass basis. And in that 80%, all the hydrogen forms methane. So we have 28 kg of hydrogen which will be converted to biogas, and all the hydrogen forms methane. And we have also seen in the anaerobic digester that hydrogen forms methane directly. And there are two pathways to formation of methane. First is the from acetate to acetate converts to methane, and the second pathway is that hydrogen reacts with CO2 to form methane. So all of the hydrogen is converted to methane. So it is given that all hydrogen converts to methane. So methane produced by this pathway, that is from hydrogen, will be 28 into 16 divided by 4. 16 is the molecular mass of methane, and 4 is there because we have 4 number of hydrogen one uh, in 1 mole of methane. So after calculating, we are getting it as 112 kg. Next, we will use carbon used for methane production. It will be 112 kg of methane which is used into 12 upon 16, because we have seen in the anaerobic digester reaction, in anaerobic digester, that methanogenesis takes place two route. First is the hydrogen to methane by use of CO2, and next is the uh, next is acetate to methane. So while formation of methane by hydrogen, around 112 kg of methane is produced, and for each mole of methane CH4 we have 12 grams of carbon, and so that's why in a 112 grams we have 12 grams of carbon, and the total mass is 16. So we will use how much of carbon we have already used. So it is coming out to be 84 kg. Okay. So next we will use the carbon that will be used for CO2 production. It will be total, we have 240 kg, and 84 kg is used for methane production. So it's coming out to be 156 kg. So now we will see how much of CO2 is produced. So we have total carbon used for CO2 production is 156 kg of carbon is used, and the molecular mass of CO2 is 44 grams, and each mole of CO2 we have 1 mole of carbon, so it will be 44 by 12. So this is coming out to be 572 kg. of CO2 produced. So total biogas produced, it consists of CO2 and methane. So we have produced 112 kg of methane and 572 kg of CO2. So which is coming out to be 684 kg. So let's see. 684 kg. So B is the correct answer. So in this question, we were given the elemental composition of the food grain, the solid content of the food grain, and also the daily flow rate of the food grain slurry. So from the flow rate, we will calculate how much slurry each day will be produced, and from the solid content, we will calculate how much of the dry solid we are getting, which will be converted to biogas. And from the elemental composition, we will get the overall carbon, hydrogen, oxygen, and nitrogen content. And as per the condition given, it is given that 80% is converted to biogas. So out of this overall carbon and hydrogen, only 80% is converted to biogas. So we will calculate how much of carbon and hydrogen is converting to biogas. And after that, a statement is given that all of the hydrogen is converted to form methane. Here, the second route of the acetate hydrolysis and acidogenesis of the complex organic matter to acetate, and then the conversion of acetate to methane. That path is not given. Only the path which is forming methane is from hydrogen plus CO2 to methane. So from this, we will calculate how much of the methane is forming. So we have calculated how much of methane is forming. So it is 28 kg of hydrogen. So from 28 kg, we will calculate how much methane we are getting. So we are getting 112 kg, and the and we will calculate how much of the carbon is used to produce the methane, and the rest carbon that will be used to produce CO2, and then from that carbon we will calculate how much of the CO2 is produced, and by adding the amount of methane and CO2 produced, we will get the amount of biogas produced. So it is 684 kg. So let's move to the next question. So again, it is a numerical type question. The question is, during pre-treatment, 50% of the mass of the lignocellulosic waste is converted to monosaccharides and disaccharides in the mass ratio of 3:7. The monosaccharide produce 500 gram ethanol per kg monosaccharide, while the disaccharides produce 550 grams of ethanol per kg of the disaccharide. Calculate the total yield of ethanol in kg. So we have been given that around 50% of the lignocellulosic biomass is converted to mono and disaccharides, and we have been given the ratio of this, and then we have been given what is the ethanol yield of monosaccharide and disaccharide, and we have to finally calculate the total yield of the ethanol, that how much of ethanol is produced in kg. So again, we will try to solve this question in 2 minutes, after 2 minutes. So I have joined. So let's see how to solve the question. So first let me share my screen. So, so this was the question. So we have to calculate the amount of ethanol produced. So let's see. So first we will have to take basis. So we will take basis as 100 kg of lignocellulosic biomass. Or it is given waste, so let's take it as waste. And around 50% is converted to monosaccharide and disaccharide. So monosaccharide and disaccharide will be this is 50% of 100 kg, so we will get 50 kg. And now the ratio of monosaccharide to disaccharide is given as 3:7. So mass of monosaccharide will be it will be 3 by 10 into 50, that is 15 kg, and mass of disaccharide, it is 7 times 3:7, so 7 by 10 into 50, which is 35 kg. And now the yield for monosaccharide and disaccharide is given. So monosaccharide produces 500 gram ethanol per kg of monosaccharide. So ethanol production by monosaccharide, so in for 1 kg we are getting 500 grams of the ethanol. So from 15 kg, so we will get 15 into 500 divided by 1000, because this value is in 100. So it is coming out to be 7.5 kg of ethanol. Next we will see ethanol production by disaccharide. It is 550 gram per kg of the disaccharide. So we have 35 kg into 550 upon 1000. So let me calculate this. So we are getting 19.25 kg. And we have to calculate the total yield. So total yield of ethanol, it's going to be 7.5 plus 19.2, sorry, 25, which is coming out to be 26.75 kg. So B is the correct answer. So in this question, it was given that 50% of the mass is monosaccharide and disaccharide. So we will calculate that, and then based on the ratio of monosaccharide and disaccharide, we will calculate how much is monosaccharide and how much is disaccharide. And after that, we will, based on the yield from monosaccharide and disaccharide, we will calculate how much ethanol we are getting from monosaccharides and how much ethanol we are getting from disaccharide. And after calculating that, we will add these two and we will get the total yield of the ethanol from the lignocellulosic biomass. So let's move to the next question. So again, it is a numerical type. The question is, a food waste is digested through thermochemical as well as biochemical routes. In the first case, the energy requirement is 28% higher than the second case, whereas the sugar production per unit mass of food waste is 22% more in first case than that of second case. The pre-treatment energy efficiency for thermochemical route is dash percentage of that of biological routes. So we have been given how much energy is requirement for thermochemical and biological routes and how much in uh, how much sugar is produced from these two routes. So we have to find out how much is the pre-treatment efficiency for thermochemical routes to that of biological routes. So again, we will see how to solve this question in 3 minutes. So let's see how to solve this question. So the pre-treatment efficiency, energy efficiency is given as where use the pre-treatment energy efficiency TSY is total soluble sugar yield. This is in kg. Efficiency is in kg per megajoule. And TEC is total energy consumption during pre-treatment, which is in megajoules. So this is the formula through which we will solve this question. So now we will have to consider a basis. So we will consider basis as 100 kg of food waste. So it is given that the thermochemical route requires 28% higher energy than the biochemical route. So biochemical route will use X megajoule of power and produce Y kg of sugar from 100 kg of the waste. So we have assumed that the biochemical route will produce X megajoule of power. It will use X megajoule of power and will produce Y kg of the sugar from 100 kg of the waste. So the thermochemical route so it's using 28% higher than the second case. So it is using 1.28 X megajoule of power and it is producing 22% more sugar than the biochemical route. So it is using 1.28 times X of megajoules of power and produces 1.22 Y kg of sugar from 100 kg of waste. So let's go to the next slide. So we will find out the pre-treatment efficiency. First will be for the biochemical, and we have seen in the formula that pre-treatment efficiency is the ratio of sugar produced, which was y, and to the energy used, which was m. So it was y by x kg per megajoule. And for thermochemical route, pre-treatment efficiency will be, it was 22%, it was giving 22% more sugar, it was, so it was 1.22 y, and it was using 28% more energy, so it was 1.2 times of the energy used by biochemical route. So after solving this, we are getting 0.953 y by x of megajoules. So we have to find out how much percentage is. So if we will convert in percentage, so thermochemical route is 95.3% of that of biochemical route. So biochemical is more efficient here. So it was 95.3%. So C is the correct answer. So in this numerical, we have to find out the pre-treatment efficiency. How much is the pre-treatment efficiency of thermochemical route as respect to the biological route? So we were giving how much that the thermochemical route was using 28% more energy, and it was giving 22% more sugar. So we will assume the sugar production and the energy consumption in the biochemical route, and then we will find out the sugar production and energy used for the thermochemical route, and then after putting it in the formula of pretreatment energy efficiency, we will find out how much is the thermochemical route of that of the, how much percentage is the thermochemical route of the biological route. So it is coming out to be 95.3%. So let's go to the next question. So the question is, during the trans-esterification process, alcohol such as methanol reacts with the dash to form fatty acid alkyl esters and glycerine. So it is the definition of the trans-esterification only. So it reacts with triglyceraldehyde oil contained in plant oil, beef animal fat, C recycled grease, or D all of the above. So we will see the solution in 3 minutes. So also I can see a participant. So please try to write your answer in the chat box, and then we will see which is the correct option. So the correct answer is all of the above. So we can see from this photo that during process of transesterification, alcohol reacts with triglyceride oil contained in plant oil, animal fat, or recycled grease to form fatty acid alkyl esters, that is biodiesel and glycerine. So this is the whole transesterification process. So here T is the correct answer. That is all of the above. So let's move to the next question. Okay. So the question is the conversion of free fatty acid can be determined from the following equation. Here S naught is initial acid value and Si is the acid value at some reaction time. So we have to find out uh, the formula for conversion of fatty acid, free fatty acids. So we have been given three formulas. So I'll wait for 2 minutes and then we will see which is the correct option. So the correct option is A, that the free fatty acid conversion is given as initial acid value minus final acid value divided by initial acid value. So here we can see that the conversion of free fatty acid is given by this formula. So A is the correct answer. So let's move to the next question. So the question is acid value is calculated as we have been given four formula and the slide which we have seen just now. So we can see here that the acid value can be calculated by using this formula, that is acid value is given as 56.1 VC by M, where S is the acid value into milligram KOH per gram and C is the concentration of the KOH used, that will be in mole per liter, V is the volume of the KOH used and M is the mass of the sample analyzed. So we can find out the acid value of a sample, like how much base it requires to get neutralized by using this formula. That is 56.1 VC by M. So A is the correct answer. So let's move to the next question. So the question is, in trans-esterification process, the plant oil which contains less than dash percentage of free fatty acid is first filtered and then pre-processed to remove water and other contaminants. So whether it is 4, 10, 15 or 20%. So we will see the solution in 2 minutes. So here we can see that in trans-esterification, the plant oil which contains less than 4% of free fatty acid is first filtered and pre-processed to remove water and other contaminants. So A is the correct answer. So let's move to the next question. So the question is, select the factors which affecting the performance of trans-esterification process. A, reaction temperature, B, reaction time, C, free fatty acid content, or D, all of the above. So we will wait for 2 minutes and then we will see which is the correct option. So the factors which affect the performance of transesterification is our reaction temperature, reaction time, free fatty acid content. So D is the correct answer, all of these. So these are the factors which affect the performance of transesterification process, which are reaction temperature, reaction time, alcohol to oil mole ratio, catalyst concentration, free fatty acid content. Next is mixing, water content, type of alcohol, and catalyst types. So let's move to the next question. So the question is, match the following feedstocks with their catalyst used for production of biodiesel. So we have been given three different feedstock, that is sunflower flower oil, soybean oil, babasu coconut oil, and their three catalysts are given. So we have to match the feedstock with the catalyst used for production of biodiesel. So again, I'll give you 3 minutes to read the question and write your correct answer in the chat box. So here we can see that for sunflower oil, the catalyst used for biodiesel production is strontium oxide, and for soybean oil, potassium carbonate or titanium oxide is used. And for Babasu coconut oil, sulfonated iron amber list 15 sulfonated ion exchange resin is used. So the correct answer is C. So we'll go to the next question. So the question is, which of the following is not a type of viscometer? Ostwald viscometer, bubble viscometer, Newton viscometer, or rotational viscometer? So I'll give you 2 minutes. Just take your time and write the correct option in the chat box. Then we'll see which is the correct option. So here we can see from the slide the various types of viscometer are Ostwald viscometer, falling sphere viscometer, falling piston viscometer, oscillating piston viscometer, vibrational viscometer, rotational viscometer, and bubble viscometer. So here Newton viscometer is it is not a type of viscometer. So C is the correct answer. So let's move to the next question. So uh, here we have been given a flow chart. In the following flow chart of biodiesel production from mixed waste plant oil, identify A and B. So we have to identify what is A and what is B. So four options are given. So again we'll wait for 2 minutes and then we will see which is the correct answer. This is the flow chart for biodiesel production from mixed plant waste plant oil. So we can see that first the waste oil, it is screened and the waste oil is cleaned. Then it is feeded in the tank, and then methanol is added, and then the A is the esterification reaction where esterification takes place, and from that we get the glycerine. So here the glycerine goes to the glycerine separator, and next we get the crude biodiesel the product goes to the crude biodiesel tank, and then the biodiesel is further processed. So A here is the esterification reactor and B is the crude biodiesel tank. So B is the correct answer. So let's go to the next question. So the question is, the current sequence of operations involved in butanol recovery by adsorption is. So this is the figure which is given. So we have to identify what is A, B and what is C. So we will see which is the correct answer in 2 minutes. So this is a adsorption setup for recovery of butanol. So here it is a fermenter. From fermenter, the butanol with all the contaminants goes to the adsorption column, where butanol is adsorbed on the adsorbent, and then the after the exhaustion of the after the column is exhausted, it is regenerated, and some desorption material is used, like some desorption material are used, like here it is heating is done to get the butanol from the adsorbent end. So A here is the fermented, B is the adsorption column, and C is the regeneration column. So B is the correct answer. So let's go to the next question. So question is, dash reaction converts plant oil to biodiesel? A. Transesterification, B. Saponification, C. Fermentation, or D. Hydrolysis. So again we'll wait for 2 minutes and then we'll see which is the correct answer. So the correct answer is transesterification, which converts plant oil to biodiesel. So, so A is the correct answer. So these were the questions based on previous year assignment, and this was the week 7 problem solving session based on week 7 material. So we will have one more problem solving session on next Saturday, and that will be all for this course. And hope you all have enrolled for the exam. So if you have any doubt, then you can ask, or otherwise we can end the session here. So okay, I
Thank
think
you.
there is no doubt. So thank you so much for joining. Have a nice day.